স্যার জয়েন করেছেন?
ও আচ্ছা আচ্ছা আচ্ছা, স্যারকে ইয়ে করো।
হ্যাঁ হ্যাঁ, সে করে দিয়েছি আমি।
আচ্ছা আচ্ছা আচ্ছা, হ্যালো, স্যারের ছবি পাচ্ছি না। হ্যালো,
ছবি স্যার ভিডিও অন করেননি, করেছিলেন
আচ্ছা
একবার, তারপরে এখন জয়েন
আচ্ছা আচ্ছা,
করেছেন। হ্যাঁ
ঠিক আছে। এই স্যার জয়েন করেছেন, চলে এসো। হ্যাঁ আচ্ছা আচ্ছা, অলোক বাবু, হ্যালো হ্যালো,
হুম হুম,
বলছি স্যারের দিক থেকে সমস্যা হচ্ছে নাকি?
না না না, সমস্যা নয়।
ও আচ্ছা আচ্ছা, স্যারকে পারমিশন সব দেওয়া আছে তো? হ্যালো,
হ্যাঁ বলছি, স্যারের সাথে টেস্টিং হয়েছিল?
না হয়নি, সেই জন্য বলছি স্যারের সঙ্গে একটু ইন্টারাক্ট করে নিন।
ইন্টারঅ্যাক্ট স্যার না এলে।
ও আচ্ছা আচ্ছা, আচ্ছা চ্যাট বক্সে লেখা যায় তো, তাই না?
হ্যাঁ হ্যাঁ হ্যাঁ,
আপনি লিখুন না, কি লিখতে হবে আমি তো।
আচ্ছা দেখছি। স্যারের ভিডিও দেখতে পেয়েছিলাম।
আচ্ছা আচ্ছা
হ্যাঁ, স্যার জয়েন, স্যার আসুক তারপরে।
আচ্ছা
হুম
আচ্ছা
হুম।
আচ্ছা আচ্ছা, ঠিক আছে।
আসিদা স্যারকে প্রেজেন্টার হিসাবে জয়েন করানো আছে।
আচ্ছা আচ্ছা, আমি এসব বুঝি না তো, আমি জাস্ট, ঠিক
স্যার
আছে ঠিক।
শুধু ওপেন।
আচ্ছা আচ্ছা, স্যার মনে হয় তো 30 বাজলে হয়তো আসবেন, এরকম আর কি। ঠিক আছে, তনুশ্রী এসে গেছে।
চলে আসিদা,
হ্যাঁ
স্যারকে একটু বলি লিখো না স্যার, মানে প্রেজেন্টেশনটা একটু টেস্ট করার জন্য।
হ্যাঁ হ্যাঁ,
সেটা একটু লিখে দাও চ্যাটে, স্যার যদি করে তাহলে আমরা করে দিচ্ছি।
আমি স্যার চ্যাটে লিখলে স্যার পাবেন তো না?
হ্যাঁ, স্যার যদি দেখে পাবে না, এটা
কি লিখবো বলো প্লিজ?
সাবু স্যার
লিখবো বলো?
স্যারকে অনলাইনে আসতে বলো, এটা আর কিছু
আচ্ছা
না।
আচ্ছা আচ্ছা।
Okay, madam already joined.
আচ্ছা
Asita, or you can actually call sir.
আমি স্যারকে লিখলাম ফোনে।
You can that we are already ready, sir. You can actually just check your presentations. বলতে পারো না,
আচ্ছা দেখছি।
তুমি সাউন্ডটা অফ করে কথা বলবে স্যার।
আচ্ছা আচ্ছা।
ওকে। আশিস দা Ashish sir,
Yes,
you can talk to the Sabu sir.
I have done.
Okay. Actually, he just actually joined the session but not present because he have to share his screen.
Ashish sir, I'm audible?
Yes, sir. Yes, sir.
Okay. Ashish sir একটা মিউটে আছে যদিও।
Yes, sir.
আচ্ছা,
You are audible.
ওকে স্যার, আমি ওটা কিন্তু হোয়াটসঅ্যাপে পাঠিয়ে দিয়েছি।
I have seen and I will give you the final format.
আচ্ছা,
Final version.
আরেকটা তনুশ্রী ম্যাডাম তো জয়েন করেছেন। তনুশ্রী ম্যাডাম একটু হ্যাঁ, যখন ম্যাডাম টাইম হয়ে যাবে না তখনই কিন্তু ক্লোজ করবেন, কারণ অনেকে দূর দূর থেকে আসে, তাদের লাঞ্চে যেতে হয়, ঠিক আছে? একটু টাইমটা মেনটেন করুন, নাহলে ডিসকাশন উইল গো অন। যদি টাইমের পরে কোনো কোশ্চেন থাকে বলবেন, আপনি চ্যাট বক্সে পাঠিয়ে দিন, উইল আনসার দ্য কোয়ারিজ, ঠিক আছে? আচ্ছা, এবার আশিস স্যার বলুন, আপনি ওই একে প্রফেসর সাবু থমাসকে কি করে ইন্ট্রোডিউস করাবো?
তো প্রথমে ওই তনুশ্রী ম্যাডাম আপনাকেই বলবেন যে স্যার আপনি
ইন্ট্রোডিউস করানোর জন্য তো?
হ্যাঁ, তারপরে আপনি করলেন, তারপরে তনুশ্রী রিড আউট করবে সিভি।
ওকে, দেন আই উইল রিকোয়েস্ট হার টু রিড আউট দ্য বায়োডাটা অফ দ্য স্পিকার।
হ্যাঁ,
ওকে
ওকে
ওকে ওকে ওকে।
এসএম স্যার কি অনলাইন এসে গেছেন?
স্যার অনলাইনে এসে গেছেন?
হ্যাঁ
হ্যাঁ,
হ্যাঁ,
দেখেছি।
এসে গেছেন, এইবারে জাস্ট এই অডিও ভিডিওটা অন হবে আর কি।
When is the talk scheduled for Professor Sabu Thomas?
Sir, it's been scheduled now only.
Hello.
Yes, sir. My voice is audible. Hello.
Sir, already joined.
Okay, madam, please start. This is already time.
So good afternoon, all the dignitaries and participants and my dear colleagues. We have come to the second session of the first day program of the online FDP. The second session will be delivered by Professor Sabu Thomas. He is Vice Chancellor of Mahatma Gandhi University, Kottayam, Kerala, India. Now, I will request our Director Sir, Dr. Prabhas Bose, to welcome Sir.
Sir, on behalf of Atal Academy sponsored Faculty Development Program on Advanced Materials and Engineering being conducted jointly by the Department of Computer Science and Engineering and Department of Physical and Material Science of College of Engineering and Management, Kolaghat, I heartily welcome Professor Sabu Thomas, Vice Chancellor, Mahatma Gandhi University, Kottayam, Kerala, India. The eminent speaker will be speaking on the topic new opportunities in sustainable materials. Good afternoon, sir. Now I request Professor Tanushree Jana to read out the biodata of the speaker. Thank you, sir.
So as Sir have already mentioned on the topic which Sir will be delivering, Professor Sabu Thomas is the Professor of Polymer Science and Engineering, School of Chemical Science, and the Founder Director of the International and Inter-University Center for Nanoscience and Nanotechnology, and full-time Professor of Polymer Science and Engineering at the School of Chemical Sciences of Mahatma Gandhi University, Kottayam, Kerala, India. He is an outstanding leader with sustained international acclaims for his work in polymer science and engineering, polymer nanocomposites, elastomers, polymer blends, interpreting polymer networks, polymer membranes, green composites and nanocomposites, nanomedicines, and green nanotechnology. Dr. Thomas groundbreaking inventions in polymer nanocomposites, polymer blends, green bio nanotechnological and nanobiomedical sciences, and he have made transformative differences in the development of new materials for automotive, space, housing, and biomedical fields. In collaboration with India's premier tire company, Apollo Tires, Professor Thomas group invented new high-performance barrier rubber nanocomposite membranes for inner tubes and inner liners for tires. Professor Thomas has received a number of national and international awards, which including Fellowship of the Royal Society of Chemistry, London MRSI Medal, Nanotech Medal, CRSI Medal, Distinguished Faculty Award, and Shukumar Maiti Award for the best polymer researcher in the country. He is in the list of most productive researchers in India, and according to recent analysis by Stanford University, USA, ranks number 2 in the area of polymer science from India. Very recently, Professor Thomas has been conferred honoris causa, that is the DSc, by the University of South Brittany, Lorient, France. Professor Thomas has published over 700 peer-reviewed research papers, reviews, and book chapters. He has co-edited 50 books and is the inventor of 5 patents. He has supervised 76 PhD theses, and his H index is 108 with more than 56,000 citations. Professor Thomas has delivered over 300 plenary or inaugural and invited lectures in national or international meetings over 30 countries. He has established a state-of-the-art laboratory at University in the area of technology. Now, I will request Professor Sabu Thomas, sir, to take over the session.
Thank you very much. Thank you very much for the kind introduction and kind invitation for the conference. I'm really excited to be with you. And I understand that this is an AICTE supported program on advanced materials. And I congratulate all the coordinators, organizers of this meeting, and many thanks for the kind invitation from Mahatma Gandhi University. I'm very pleased to interact with you. And the title of my presentation is, I'm going to share my slide. The title of my presentation is New Opportunities in Sustainable Nanomaterials. I've been working on this topic for the last 10 years. So what we really do is, we extract. Can you all see my slide?
Yes, sir.
Yes, sir. Yes, sir.
Very good, excellent. What we do is, My research group is trying to extract nanomaterials from biological resources. My PhD students go to agricultural production land, collect the material, the waste from these agricultural production units, and then transform them into nanomaterials. Those who want to know more about my activities, you can look at my website, sabuthomas.com, iiucnn.mgu.ac.in. According to American Chemical Society, we have 1.6 billion tons of agro waste every year. You see, we produce lots of agro waste. And these wastes are not properly utilized. And if you don't utilize them properly, they will create ecological issues. They will decompose, and there will be a lot of smell, a lot of ecological hazards. So it's very important that we must make use of all this biological waste. It could be agricultural waste, it could be waste from the fish industry, and transform them into advanced functional materials. That is the essence of this talk. Look at the agricultural waste you get. Sugarcane bagasse. We have a large number of sugarcane factories in this country, and we produce lots of bagasse. After extracting the juice from sugar cane, the bagasse is a waste. And we know India is we are big eaters of wheat and rice, and we produce a lot of wheat bran and rice bran. We eat a lot of corn cob, wood flour, wheat and rice straw, jute, coir, pineapple, hemp, banana, bamboo, whatnot. We produce lots of agricultural waste. Look at our fish industry. We have a lot of crab shells, prawn shells. They are fantastic material for advanced manufacturing of advanced materials. Waste starch. My research group has fabricated nanomaterials from waste starch. Now, if you look at the global production of this material, this agricultural waste, you will find that wood is number one. I have shown the amount of waste we produce. Wood is number one. Bamboo, cotton lint, jute, canaf, flax, see. And these materials are not properly utilized. Look at plant fibers. They are fantastic materials. They are environmentally friendly. They are relatively cheap, non-abrasive to machineries, very good mechanical properties, low density, you have excellent, fascinating properties. It will provide lots of job opportunities for the society. And you can have fibers from bast, from the stem, fibers from the leaf, fibers from the seed of fruit, fibers from the grass. So we will have fibers from different sources. You see, Kerala is rich in banana. We have lots of pineapple plantation. We have oil palm. See, all this banana stock after harvesting is a waste. Kerala is a land of coconut trees. We have lots of industries based on coconut fiber. There also we have a lot of waste. Let us look at the mechanical properties of this material. These materials have very good mechanical properties. Look at tensile strength, Young's modulus, elongation break. Interestingly, if you look at the density of this material, the density is always 1.5, 1.25, 1.1, much lower than glass fiber. Therefore, the specific properties, property divided by density, these materials give fantastic values. It can beat glass fibers. The chemistry of this material. Essentially, lignocellulosic materials are composed of cellulose, the main component. Look at the structure of cellulose, they are fantastic hydroxyl groups. And you can do very good chemistry of the surface. The second component of the lignocellulosic fiber is lignin, a very fascinating biopolymer, green polymer, and hemicellulose. Another important point of plant fiber is you can work in different hierarchical landscapes. Look at this is a macro fiber. Look at this, a macro fiber. It could be, the diameter could be 0.5 mm or 1 mm. And inside this macro fiber, you see a large number of microfibers. See, you can take out this microfiber. Inside the microfiber, look at, you have a large number of nanofibers. So you have the possibility to work on macro landscape, micro landscape, and nano landscape. I remember when I started my job at the university as a lecturer back in '87, you know what I used to do with many companies? They used to give me small projects. I used to chop up macrofibers into shorter lengths, do some chemical treatment, mix with the natural rubber and polypropylene and make beautiful composites. But right now, what I'm going to talk today is extracting nano from these fibers, nanofibers, specifically nanocellulose. Then I'm putting a question to you. Why nanocellulose is so important? I would say this is one of the most important nanomaterial. Nanocellulose can beat with a carbon nanotube or graphene or many of the synthetic nanomaterials. And you might ask why it's so important. The answer is here. It's a strategic platform for sustainable development because it's renewable. You can extract from agricultural waste. And it is biocompatible, eco-friendly. Additionally, they provide lots of advantages. Extremely high water holding capacity, highly crystalline, high strength, low density, high specific strength and modulus, high aspect ratio. So you have fantastic, fascinating properties. If you look at nanocellulose with your naked eye, if you put nanocellulose in a plastic container, you see, it looks like a gel. It's a gel. And if you examine under high resolution electron microscope, what you really see is a beautiful web of interconnected nanofibers. The diameter of this fiber is range of 20 nanometers. Length could be 1,000 nanometers, 2,000 nanometers. It's very difficult to measure the length of the fiber because it's very long. Then you might ask, how do you produce them from plants? You can do acid hydrolysis. You can do steam explosion process. You can do high intensity ultrasonication process. You can do high pressure homogenization process. You can do super grinding invented by the Japanese people. You can do cryo crushing. You subject the fiber under low temperature and you go for a crushing. So all this process, what we do is you apply intense shear to the system and then you remove lignin hemicellulose and split up the fiber. These are all well-known techniques. I will show you what we do in our laboratory. In my laboratory, we usually do a lot of steam explosion process. Look at this is our natural fiber. Expanded model. This has got lignin hemicellulose and nanofibers. You subject them into a high pressure temperature in an alkaline medium. 150 degrees Celsius and a pressure of 137 Pascal. And during this steam treatment, you steam it for about 20 minutes, 25 minutes at high temperature and pressure. Then you release the pressure suddenly. Then you have an explosion taking place. Why it's called steam explosion? That is what we call steam explosion. When the explosion takes place, you know, you have a lot of opening up. You see, the fibers are sort of opened up. And you can remove lignin hemicellulose by acid hydrolysis. And you get beautiful nanocellulose. You know what I do in my laboratory? We collect agricultural waste first. This agricultural waste is alkali treated. We do bleaching. We remove lignin hemicellulose. We get a slurry, and the slurry is subjected to mild acid hydrolysis or strong acid hydrolysis. If you want to have nanocellulose, long nanocellulose, we subject them for mild acid hydrolysis coupled with the steam explosion. When you go for a homogenization, you know what we get? We get the dispersion of nanocellulose in water. And we examine under electron microscope, you see, you get a beautiful network of nanoscale fibers having a diameter of 20 nanometers. Let me quote some of the work. Professor Shu and co-workers, what they did is, they subjected plant fiber into acid hydrolysis and steam explosion process. You know what they've made? They've made two types of material. One is long nanocellulose. When the acid they used is mild acid, you see, this is a long nanocellulose. You have crystalline, amorphous. Crystalline, amorphous. But when Professor Shu used strong acid, you see, the strong acid could eat away all the amorphous region. This is amorphous region, and he got short nanocrystals. So you can get either long nanofibers or short nanocrystals. You can see this picture, the totality of the process is given in a sort of schematic. And the beauty of this material is, the Young's modulus of this material is 130 gigapascal. And the strength of the material is 10 gigapascal. It's a fantastic material. Let me show you the work of Muhammad from Europe. Muhammad made use of wood flower. I'm showing the bark of a wood. I've shown a small section here. This is the plant cell, and then you have different length scale. And he used very strong acid, 65% sulfuric acid, 45 degrees Celsius treated. You know, he got short nanocrystals acid hydrolysis. You can see Professor Shu produced beautiful pointed nanocrystals by sulfuric acid treatments. Let me show you what we have in our laboratory, NGU laboratory. Mahatma Gandhi University laboratory, we have a small plant. We are going to scale up, and we are starting a company in the campus. We do steam explosion of raw banana fiber in alkaline solution, bleaching of the steam exploded mass, followed by acid hydrolysis. And this is our setup. You can see the plant fiber. We have a steam explosion process, bleaching process, acid hydrolysis, and finally we get beautiful nanofibers. You see? We get beautiful nanofibers. Let me also show you the dynamics of the enrichment process. What happens each stage? When my PhD students collect raw banana fiber from the plantation, you see the raw fiber has a cellulose content of 64%, hemicellulose 18.6%, and lignin 4.9%. When we do steam explosion process, acid washing and bleaching, you know, after steam explosion process, the cellulose content is increased to 92.37, and you see the hemicellulose is decreased, lignin is sort of washed away. When you continue the process and after the bleaching, you see, you get a material which has a high content of cellulose, nanocellulose. My PhD student produced up to 98% of nanocellulose. I wanted to show you some beautiful AFM picture of my PhD student. He went for a postdoc in Israel, followed by a new postdoc in US. He's staying back in the US. He's Eldo Abraham. He has made beautiful nanocrystals from banana stalk. You see in the range of diameters in the range of 25 to 30 nanometer. Short nanocrystals by acid hydrolysis. Let me show you another work. We had a very long cooperation with Sweden. Professor G.P. Matthew, a student of mine, went to Sweden, and we made nanofibers from wood flower. Look at this. Atomic force microscopy picture. This is our Brazilian collaboration. We had a India-Brazil joint cooperative program under DST, and my PhD student made nanofiber from pineapple leaf fiber, and you see this is a FESEM picture of nanofiber. Now I wanted to show you one of the drawbacks of nanocellulose is its polar surface, and its dispersion in non-polar polymers are very poor. Look at, I got a new project with Apollo tires. They wanted to incorporate nanocellulose into tire tread and tire sidewall. Particularly, we focus first on tire tread. When you mix nanocellulose with SBR rubber or natural rubber, there is a big question of incompatibility. Therefore, in order to overcome these incompatibility issues, in order to overcome this, dispersion issues, especially with the non-polar polymers, one has to do surface chemistry. Because look at the structure of this material. We have fantastic hydroxyl groups. So you can do tempo oxidation. The OH could be converted into COH. You can do esterification reaction. You can do polymer grafting. Polymers could be grafted on the surface of nanocellulose. You can label fluorescence group on the surface of nanocellulose, and you can do fantastic fluorescence spectroscopy study. And one group in Canada made beautiful sensates. You can do cellulation reaction. This is what we are going to do with Apollo tires, cellulation reaction to make them hydrophobic. You can do cationization reaction. So several chemical reactions could be performed on the surface of nanocellulose to overcome the issues of dispersion, to overcome the issues of incompatibility, to overcome the issues of poor interfacial adhesion with non-polar polymers. Let me now show you what we do in our laboratory. My laboratory, my PhD students, we do advanced functional materials using nanocellulose for water purification. I'm going to show you maybe a couple of slides on water purification. I'm going to show you some work on wound healing, some work on EMI shielding, some work on sensors. Let us see how nanocellulose could be utilized for water purification. We all know that water is increasingly contaminated by different types of pollutants, bacteria, virus, heavy metals, different types of dyes, suspended particle, and UN says that there could be fight for water. So water is going to be a very scarce material. So there is every need to work out methodologies to purify impure water. Our methodology is very simple. You can see our protocol. What we do is we make use of commercial membranes. If you look at commercial membranes have a sort of bilayer construction. The bottom part is non-woven microfiber support, and over which you have a nanofiber support, which is basically PVDF, electrostatic PVDF. This is nanofiber. So what we have done is we have given a coating of nanocellulose on the surface of commercial tissues. This is our hydrophilic coating. Look at this. So we have given a coating.
కూర్చోవడం మస్తు కష్టం కదా ఎవరైనా హెల్ప్ తీసుకోవచ్చా
I request everyone,
తీసుకో ఎవరు కావాలంటే వాళ్ళు తీసుకొచ్చి
అంటే నేను చెప్తే బాగా
please mute.
నేను చెప్తే బాగోదు కదా
నిరోష ఐపీ నిరోష ఉన్నా నిరోష నా అమ్మాయి శ్వేత కొంతమందిగా తీసుకో సార్ చెప్పినట్టు చెప్పు.
It was organized to take care of.
వాళ్ళిద్దరు తీసుకో.
So removal of dyes, removal of nanoparticles, removal of heavy metals, oil, bacteria, virus. It's a fantastic material. I will show you what I've done with my PhD student, Kumar. Look at this. This water coming from a textile industry, it is highly colored and contaminated with crystal violet. Crystal violet dye is a textile dye being used by many industries. So we thought of working on the removal of crystal violet dye from water. I will show you the protocol what we have used. You see,
అవి రాసుకున్నాం అదే చేస్తున్నాం కాకపోతే కొంచెం సిమిలర్ చెప్పండి
we made nanocellulose.
మనం పీక్ ఉంది కదా
Made nanocellulose.
కాదు పీక్ ఉంది కదా ఇప్పుడు ఏ దానికి పీక్ వేరే వస్తుంది బి దానికి వేరే వస్తుంది సో నేను ఏం చేస్తున్నా పీక్ ఇంటెన్సిటీ పెట్టుకుంటే వెళ్తా పెట్టుకుంటూ వెళ్ళిన తర్వాత సిమిలర్ గా ఉన్నవి నంబర్ అటు అడ్జస్ట్ చేసి 60 నంబర్స్ మీకు ఇచ్చేస్తాం
I request organizers.
మండే రోజు
I cannot speak otherwise. Please go on mute. When I speak, I request everyone to go on mute.
సెకండ్ ఇయర్ ద సెక్షన్ ఓకే
You can see this is our nanocellulose, which is chemically modified. I will show you a small chemistry we have done. My PhD student did a small chemistry. You see, this is our nanocellulose, which is chemically modified with the meltron acid. So we have CO minus group on the surface. This is the dye from the textile industry. And this dye can form some sort of electrostatic interaction. And you see, this is our filter we have designed. When we put this water to our filter, to our beautiful filter, you see all the dye particles are being treated. And the reason is because these dye can form an electrostatic interaction with the nanocellulose. You see our dye removal. You can see this paper from ACS. We published in ACS. This is absorption capacity as a function of time. This is the commercial filter. This is a filter modified by us with nanocellulose. The top one is chemically modified nanocellulose. Look at this. So chemically modified nanocellulose, if you make and if you give a coating on the surface of commercial filters, you can get fantastic results. Now let me show you another important slide where my PhD student and I, we worked together and we found that this filter is extremely beneficial to remove suspended particles in water. You know, water has a lot of suspended particles. Look at these are all iron oxide particles, metallic particles. And when we filtered this water having lots of suspended particles, we found that, you see, all the suspended particles were retained at the top of the filter. And this is the bottom part of the filter, which is made of PVDF. Look at this. Our filter is capable of removing all the suspended particles. What we have removed is iron oxide particles in the range of 50 nanometer size. And I have a transmittance data here. This is the feed solution, which is very black because you have lots of iron oxide particles. And you look at the transmittance, light cannot transmit because you have lots of nanoparticles. There is a lot of scattering. When you do the filtration process, you can remove all the particles. All the particles are retained by the filter, and you see you get good water. Look at the transmission; it's almost 100%. So my message is, nanocellulose coated filters are extremely beneficial to remove suspended particles from water. Nanocellulose is again extremely useful to remove oil from water. You know, you all might be reading the newspaper. Seawater is increasingly polluted because of the spillage of oil from the ship. Several ships get damaged. Sometimes they are sunk. And sometimes because of the damage, the oil is leaked into the seawater, and the seawater is increasingly contaminated with oil. And there's a beautiful work by Kottayam and group from Finland. You know what they did? They made nanocellulose aerogel. If you want to manufacture aerogel, it's a very simple process. You take nanocellulose and water and you go for a freeze-drying process. You can get aerogel. And then the group did something interesting. See, this aerogel is extremely hydrophilic because nanocellulose is hydrophilic. You know what they did? They gave a coating of titanium dioxide on the surface of nanocellulose. Look at this. You see? Once you give a coating of nanocellulose surface of coating of the air to the surface of nanocellulose, it becomes hydrophobic. And then you put in water. Nanocellulose become resistant to water. You see? So all the oil is absorbed by the cellulose. Water cannot get in because it's hydrophobic. And then you know what you do is the oil is absorbed and you press it and you reuse the oil. Or you can burn. So this is a way we can purify seawater. Kottayam and group suggested that you make nanocellulose aerogel and you sprinkle in seawater, collect it after a while. And this way we can remove oil from water. You can also remove bacteria. You can also remove chromium. You can remove lead. You can remove copper. Many heavy metals could be removed from water. Even northern part of India, northeast of India, water is increasingly contaminated with heavy metals. Here are fantastic data. Professor Wang and group from China, what they did is, they tried to remove chromium from water. You see, this is a chromium absorption as a function of time. You see, there was beautiful absorption of chromium by nanocellulose. But please remember the fact that if you want to remove chromium, you have to do a little bit of surface chemistry on the nanocellulose. Then they made an amidation reaction. You know, in the amidation reaction, what they did is they introduced massive amount of amine group on the surface of the nanocellulose. So nanocellulose became electropositive. And this electropositive nature of nanocellulose, high positive charge density on the nanofiber surface, led to the efficient absorption of negatively charged chromium-6 ions. I can show you another important slide. Nickel could be removed, nickel 2, cadmium 2, lead 2, all these things will be removed. This is basically because acid hydrolysis of cellulose nanofiber provides negative charge so that nickel, cadmium, they all have positive charge, so you can have electrostatic interaction. So if you look at this rice straw, cellulose fiber, nanocellulose, see, nanocellulose is much more efficient. So friends, cellulose is a fantastic material. You can remove heavy metals. You can also remove bacteria, viruses. Bacteria and viruses could be removed. And you know, these bacteria create lots of trouble: cholera, dysentery, typhoid fever, and we are all suffering from the pandemic or viral pandemic, the coronavirus. And all these things could be removed by using nanocellulose membrane. We want to remove bacteria. Bacteria are bigger in size. So they will not pass through the holes of this membrane. So bacteria could be retained by the membrane beautifully by size exclusion. But viruses are small. If you want to remove virus, again you have to do a small chemistry. You react with polyvinylamine, as I mentioned. So you introduce large number of amino group on the surface of nanocellulose. So you get positive charge. And you all know that viruses have a protein envelope which is negatively charged. And there could be electrostatic interaction between the virus and the so you can remove that. You can remove viruses. You can remove bacteria. Only thing is you have to properly do a good chemistry. You can see the logarithmic reduction values of different types of microbes. We have another interesting picture here. This is an excellent scaffold material. You can see a gentleman suffering from high degree of burns on his face. And his face is completely covered with nanocelluloids. You see? And the tissue growth, tissue regeneration is very efficient because it's extremely porous. There are porous structure. Tissue growth and tissue regeneration is very efficient. And I want to show you some interesting data. We have been very active with the Brazilian University in Sao Paulo. My Brazilian counterpart was very active in making medical grade polyurethane for heart valve. And 17.5 is the tensile strength and E modulus is 37.5. When he visited us, he said, why can't we use nanocellulose from pineapple fiber for manufacturing of polyurethane cellulose heart valve prosthetic material? So he said, then we said, why not? We introduced nanocellulose in the polyurethane. Look at the quantum jump we got. 37.5 became 992.4 megapascal, the modulus. So he was really interested in this data. You know, ultimately what we did with the Brazilian corporation, the Brazilian hospital, they did lots of animal studies, and eventually they made nanocellulose polyurethane prosthetic heart valve. And we published a series of papers. Nanocellulose is an excellent material for wound healing. The excellent platform for sustained release of antibiotic. I wanted to show you the nice work of Sebastian Moritz. Sebastian Moritz, you know, they introduced antibiotic into aerogel of nanocellulose. They made aerogel. They made use of bacterial nanocellulose and aerogel. And from this aerogel, you can see the release profile. The antibiotic is released in a sustained fashion. You see? And they have concluded that it's a fantastic wound dressing material with a controlled drug delivery process. Lu and Cover case from China, there is some interesting one. Combined nanocellulose with collagen. They made a hybrid configuration, nanocellulose and collagen, and they made composite aerogels. And when they combine nanocellulose with collagen, you know, became more compatible, highly biocompatible. And look at the density, 0.02 to 0.03 gram per centimeter cube. And porosity is 90 to 91%. Water absorption went up to 4,000. They made fantastic lightweight material. And Professor Lu and group suggested that this is a fantastic material for wound dressing and tissue engineering stuff. Nanocellulose is again a fascinating material to reinforce typical commercial filters. Commercial filters made by electrospinning, for example, polyacrylonitrile filters made by electrospinning, is mechanically weak. So, if you look at the work of Professor Kao, he suggested that if you reinforce these commercial filters with nanocellulose. Look at this. This is a single layer coating, this is a double layer coating. The mechanical properties are substantially improved. If you give a coating on one surface, the mechanical property went up to 10 megapascal. Double layer, it went up to 13.5 megapascals. So commercial membranes could be strengthened by coating nanocellulose. Let me show you what we have done during the Corona time. We wrote a very interesting proposal with Georgia Tech in the United States, with the lots of universities in the country, with some hospitals. We designed a new mask. And this mask has 3 layers. The outer layer is made of polyester with an anti-adhesive coating. And this anti-adhesive coating can repel coronavirus. It's a polyelectrolyte coating. And the middle layer is made of nylon, which is electrospun, coated with positively charged nanocellulose and curcumin. This is a combination of the middle layer. And the innermost layer is nothing but cotton, very close to the mouth. It's more eco-friendly, and this is also coated with a little bit of curcumin. So if coronavirus is coming, this coronavirus could be repelled by this outer surface because it is an anti-adhesive coating, polyelectrolyte coating. And the middle layer is nanocellulose, which is positively charged. If at all some coronavirus is getting in, because sometimes people are very careless in wearing the mask, this coronavirus could be killed by this nanocellulose because it is positively charged. And this has also got antiviral coating of coating. So this is a design we proposed. You can see our tri-layer mask, the outer layer, the middle layer, inner layer. Let me show you a few more slides. See, my group is quite active in making sensors, making EMI shield aids. I will show you some of that. Look at this work of Professor Wang. You know, he mixed CNDs and nanocellulose together, and then went for a sonication process, mixed it with the natural rubber latex, went for hot pressing, and made beautiful a hybrid composition. It's a very interesting slide of Professor Wang. If you look at this, is nanocellulose. The zeta potential is 51.2. 0 hour, 24 hours. Very stable. 0 hour, 24 hours. 24 hours, all the nanoparticles settle down. This is 0 hour, this is 24 hour. You see? This is pretty stable. See, if you mix nanocellulose and CND together, the dispersion is stable. No settling down of CND. So CND interaction will be destroyed by nanocellulose. If you just simply take CND and if you keep it for 24 hours, all CND will settle down. So this is a new philosophy. If you mix two nanofillers together, you can get synergistic action. You can get axial dispersion. Look at this. This is CND, CNC. CND and nanocellulose and carbon nanotube in natural rubber. Beautiful dispersion. Only CND in natural rubber, they all agglomerate. So dispersion of CND in natural rubber is very difficult because CND is CND interaction. But if you mix CND and CNC nanocellulose together and put into natural rubber, you get fantastic dispersion. I have a beautiful slide here. This is CND alone in natural rubber. You get the percolation somewhere over here, 6% of CND or percolation. But if you take mixture of CND and nanocellulose together, Your percolation here, around 1.5 volume percent your percolation process. Your percolation process is 1.5 volume fraction. See, the percolation concentration of CND could be reduced by mixing CND and CNC together. Of course, you get fantastic mechanical properties too. Look at this is the neat natural rubber, and if you combine, look at this is the best one, CND, CNC together. See, look at the mechanical properties are very good. Let me now show you the energy storage application. A PhD student of mine, he made nanocellulose, and then he made hybrid structure. Nanofibers mixed with graphene oxide. We found that this is a fantastic material for energy storage. This is nanocellulose alone, and this is varying concentration of nitrogen dropped graphene oxide. You see the dielectric constant increases dramatically. That what implies this is a fantastic material for energy storage. So hybrid construction is always excellent. You get fantastic properties. Let me show you another important work of Professor Wang and group. Professor Liping Wang and group, you know what they did? They manufactured aerogel of bacterial nanocellulose. And then they went for pyrolysis, high temperature pyrolysis, and made carbon. So they have
சொல்லிட்டு இப்போதைக்கு நான் ஏன் பைசா வச்சு வாங்கிடுவேன். இது பின்னாடி கிளைம் பண்ணணும்னா இது ப்ராப்பரா நம்ம இது கொடுத்தாதான் கிளைம் பண்ண முடியும். அதனால நான் சொல்லிட்டே வந்தேன் சார், நான் கெமிஸ்ட்ரியில போய் சார்ட்ட கேட்கிறேன், உங்க பேர் சொல்லல, யார் எனக்கு அதை கரெக்டா இது பண்றாங்களோ அவங்க கேட்டுட்டு வர மாதிரி தாராளமா.
Fantastic material for lithium-ion batteries. You see, because it's extremely porous. And electrolyte-electrode interaction is very strong because it's a porous material. So Professor Wang and group made anode material for lithium-ion batteries using nanocellulose. Let me show you some of the work we have done in our laboratory. Look at my PhD student made nanocellulose from banana plants. He went to the banana plantation, collected the waste, did acid hydrolysis and made nanocellulose long. Then he mixed with aniline and went for in situ polymerization process. He made polyaniline nanocellulose composite material. And you can see the atomic, SEM picture of this material. And this is the totality of the process. He made nanocellulose dispersion, introduced aniline, went for in situ polymerization, vacuum filtration, and he got a beautiful nanocellulose paper. Look at these are nanocellulose paper, yes. And this nanocellulose paper is a fantastic material for EMI sheet. A beautiful material for EMI sheet. So in summary, I want to tell you that. I'm going to summarize my talk. You see, the agro waste is a fantastic starting material. You can make beautiful advanced functional materials for water purification, for EMI shielding application, for reinforcement, for packaging application, for wound healing. And I'm posing a question to all the listeners, all the people who are attending my talk. Can we become a zero waste planet? The answer is yes. We have utilized all these waste materials intelligently with the proper chemistry. We can make fantastic advanced materials and we can make a zero waste planet and preserve our planet for the coming generation. Let me thank all my co-workers. They did a lot of work in my laboratory. Government funding, particularly thankful to Professor Sena Rao for generous funding, international funding, industrial funding, and my collaborators worldwide. They all supported me for a lot. You can see a picture of our group when Yves Groffens, our collaborator, came from France. There's a beautiful picture of our chemistry group. And you can see our the picture of our nano group. A picture of our nano group. This is me, and this is now headed by Professor Nanda Kumar. This is our nano group. So I have two groups: the nano group and a chemistry research group. And you are most welcome to Kerala. Please do visit us. Please come to Kerala for the next conference, face-to-face meeting we are going to organize after the pandemic. Some pictures of Kerala, beautiful boat and very nice pictures of Kerala. Please do visit us. This is our campus. I'm sitting in this building now as a Vice Chancellor of the university. We are polymer, organic, inorganic, physical, and hot actives. We have Center of Nanoscience and Nanotechnology. Last year, we organized a beautiful conference, international conference, 100 years of macromolecular science. Because macromolecular science completed 100 years. So we celebrated 100 years of macromolecular science in the campus. A big international meeting we organized. And we have a conference coming up. You are all welcome. This is again an online conference. International conference on nanomaterials. April 9, 10, 11, 3 days. So please do visit us. I'm an editor of Nanostructures and Nano Objects. I say that journal, no charges, it's free, no pay charges, not open access, a traditional journal, and its size code is now 6. So those who are interested in this journal, please send your nano paper into this journal. You are all welcome to submit your paper to this journal. We have very strict international review process. Thank you very much for your patient hearing. Thank you. Please ask some questions if you have.
Hello. Hello.
Hello. I welcome you.
Sir, very nice talk, sir. Actually, I was also starting my work on nano, so it was very good to hear you, sir. And also, you are teaching about cellulose. Sir, I work on carbohydrates. This targeted drug delivery. So my question is that do you have any data regarding how, if we give them orally, where this will should get degraded?
Yes. You see, what we have done is we do electrospinning process, and then we introduce the drug into the electrospin platform. That is one way. We make aerogel, and then introduce the drug into the aerogel, and then we can use for sustained release. This is what we do externally. Not only orally, but externally. We did a lot of drug delivery studies. We
Sir,
can collaborate, we can cooperate with your group. We're very happy to do that.
Okay, sir.
Thank you for the interesting question. Please visit us.
Okay.
More questions?
So I think we don't have any more questions in chat box. So if the participants have any questions, so they can mail you. So
Manju ma'am, you can ask the question. Manju ma'am.
yes. Okay, Manju ma'am will ask some question.
Okay, you can ask the question. What is your question?
Please ask.
I think she's not audible. Manju ma'am, you are not audible.
Then you can give my email ID to all of them. Let them send their email to me.
Okay, sir.
Yeah, I will answer them.
Okay, sir. Okay, sir.
Thank you. Thank you for the wonderful conference, and wish you all the best.
Thank you, sir.
Thank you. Bye-bye.
Okay, sir. So I'll announce for the participants that our next session will start from 7:30 p.m. and it will go up to 9 p.m. So please join 10 minutes before the session.
Okay, and same link. You can join the session with same link.
Thank you. Excellent.
Okay, you can join the session with the same link.
Hello. Sir, please